In this video, we're going to discuss the Monty Hall problem, which is named after the Monty Hall show, and it was a game show where at a certain point, the contestant gets to choose between 3 doors. Behind each door, there's either a prize or a goat. So you have 3 possibilities. You could get goat number 1, goat number 2, or your prize, which might be money, or it might be a car, a house, something cool that you want, but 2 bad things and a good thing. And they could go kind of anywhere among these 3 doors. Obviously, the goal is to walk home with the prize, the money, the car, whatever it is. And if you want to think about the probability of choosing the prize, we discussed before in a previous module that the probability of event A happening is the number of ways A could happen divided by the total number of things that could happen. And so in this particular case, the probability that you win the prize money is 1 over 3, because there's 1 door with prize money and 3 doors in total. However, that's not how the game works. You don't just pick a door and then they give you what's behind it. How the game actually works is that you choose a door, then the host opens one of the other doors. And that will always reveal a goat. So if you chose a goat, he will open the other goat. If you chose the prize money, he could pick either one. But the point is, he's always going to show you where one of the goats or one of the non-prizes is. And then you get to choose to move to another door or to stay. And then whatever your second choice is, that's the door you get what is behind it. So you will get the prize or the goat from behind that door in your second choice, not the first one you choose. This is slightly more complicated than the probability of just choosing the money, 1 door out of 3. And it's even more complicated than it may seem at first. At first you might seem, all right, well now my shot is 50-50. So originally we might think that the probability of, or we know that the probability of choosing the prize originally is 1/3. But now with this second choice, now that we have one of the goats eliminated, is it 1 out of 2 doors? The answer is no, and you saw that in the episode. But here we're going to describe a little bit of why. So I'm going to make a decision tree essentially for what could happen. So first I'm going to choose a door. And here I could have chosen the money, or I could have chosen a goat. The probability that I chose the money is 1/3. As we talked about before, there's 1 out of 3 doors with money. And the probability that I chose a goat originally is 2/3. There's 2 doors with goats out of 3. Then we choose to move or stay. So move or stay from each of these. If I was at the money and I stayed at the money, I win. If I was at the money and I chose to move, I lose. If I was at a goat and I chose to stay, I'm still at a goat. If I was at the goat and I choose to move, the other goat was eliminated by opening the door. So here's where you're guaranteed some money. If you don't worry about the probabilities involved, it looks like you've got now 2 out of 4 choices, which is 1/2. So it still might be probability 1/2 of winning. 2 out of your 4 final choices of moving and staying involve money. But these probabilities are actually really important. So initially there's a 1/3 choice that you chose the prize. And then moving is 1 of your 2 choices at that point. Staying is 1 of your 2 choices at that point. There was a 2/3 choice that you originally chose a goat. And so after that step, you have 1 out of 2 choices to move, 1 out of 2 choices to stay. And the way trees like this work is that when you go from the beginning to the end, so start at choose a door and follow any path to the bottom, you want to multiply the probabilities to get the overall probability of that. So 1/3 times 1/2, the probability that I end up here is 1/6. 1/3 times 1/2. 1 times 1 is 1, 2 times 3 is 6. The probability that I end up here at the prize is also 1/6, 1/3 times 1/2. The probability that I end up here is 2/3 times 1/2, that's 1/3, and the probability that I end up here is 2/3 times 1/2, that's 1/3. So here's the probability of each of your 4 outcomes. Now the question in the Monty Hall problem is, what is the winning strategy for your second choice? The first one is always going to be random. But is there a way to increase your chances of winning at the second step? So should I always choose to move, always stay? What is the ideal strategy for winning? Maybe it doesn't matter. So this is similar to some computations that we saw at the very end of the last module. These are conditional probabilities. So what's the probability that I win given that I stay? And what's the probability that I win given that I choose to move? Now we didn't go into the nitty-gritty of how to compute these conditional probabilities last time. I kind of glossed over it. But what it's going to be is the probability that I stay and win divided by the probability that I stay. It's the probability that both things in the parentheses happen divided by the given. So here, probability that I win and move divided by the probability that I move. And this sounds a little scary, but we can actually read it right off the chart that we already have. Stay and win, that's only this ending, so 1/6. So down here, the probability of staying and winning is 1/6. Similarly, we can look for the probability of winning and moving on the chart. If I am going to win, I need a $sign, and move, that's here, so 1/3. And what's the probability of staying? Well, that's everything with a stay. So that's going to be the 1/6 and the 1/3. So probability of staying is 1/6 plus 1/3. And the probability of just moving, that's all the things that end up in move, that's 1/6 plus 1/3 as well. So the probability of winning if I stay is 1/6 divided by 1/6 plus 1/3. Well, this is 1/6 plus 2/6, this is 3/6. So 1/6 divided by 3/6. Invert and multiply. This probability is 1/3. The probability that I win if I move is 1/3 divided by 3/6. So 1/3 times 6/3. So that's 2/3. And so which one has a higher probability of winning? This number is twice as big as this number. So the probability of winning if I move or switch doors after given the choice is actually twice as big as the probability of winning if I stay. Therefore, the winning strategy is to always move. You have a twice as big chance of winning if you always move. So this is some very basic probability from sort of an introductory probability course, but it's very counterintuitive. You would think once it's down to 2 doors, the probability of winning should be the same either way, half and half. But it really isn't, because you're getting so much information at this second step. When the host opens one of the other doors, you're getting information about where the money is. And so that really slants your probability of winning, and you should always move. You get a twice as high of a chance of winning if you move than if you stay. And this is precisely what Amy was trying to explain throughout the episode.